Hello, my name is Nick. Full name is Nick Stevens. I'm going to be talking about a number of TrustZone bugs in Huawei phones, also just normal Huawei kernel bugs. If you don't know what Huawei is, that's okay. I'm going to talk about it in just a second. I also want to briefly apologize for the program just has my bio as the description of this talk. I'm not just going to be talking about myself. I'm going to be talking about actual technical work, so I'm sorry if anyone's confused by that. I don't know how that happened. So the first little bit about me, I play on the Shellfish CTF team. If you're familiar with CTF, it stands for Capture the Flag. It's like a hacking competition, but more focused on actual exploit development and software vulnerability finding, less so about like pen testing. I also worked on the Cyber Grand Challenge, which is another thing that's similar to CTF, but it was run by DARPA, which is the Defense Advanced Research Programs Agency or something. They ran a competition to see who could write an automated hacking tool, a tool that could find bugs automatically and automatically write exploits for the bugs it found. So it was sort of called the self-driving car equivalent of hacking. So I worked a lot on that with Shellfish as well. And then also we published a number of research papers on subjects like automated bug finding and automated exploitation. And also I published some papers on Android bugs and just TrustZone bugs in general and the kind of problems that TrustZone can introduce. And if you're not familiar with any of these things like TrustZone, I'm going to be talking about them and introducing them to you. In general, just played a lot of CTF, and now I currently work for Raytheon CSI as a vulnerability researcher. You may have actually heard of us before. We used to go by a lot of different names, such as Raytheon SI Govs and Raytheon COI, and now it's CSI. You can just call it Raytheon. And I do this kind of work for a living that I'm about to present. If you're interested, please let me know. We're always hiring. So first of all, the goal of this talk is to demonstrate a way to completely compromise the Huawei P9. Now, the Huawei is a Chinese phone manufacturer. They're not very popular in the States, so if you haven't heard of them, don't worry. They actually have a very difficult time entering the U.S. market because of national security concerns. You can find them in the news about once a year. They often get in trouble. But besides making phones, what they also do is they'll make network equipment and sell that to other countries that the U.S. finds unsavory. Now, this is a pretty interesting target because they don't actually see as much public scrutiny. So I decided to look for bugs in it as an exercise. So what we're going to do is we're going to start from an untrusted app on your phone and completely compromise something called the TEE, which stands for the Trusted Execution Environment. Now, this is actually a special operating context on your phone that many people don't know about. It's pretty different than what most people are familiar with when it comes to security architectures between like Ring 0 and Ring 3, excuse me. But because of the number of sensitive operations that take place on our smartphones, ARM in particular and mobile manufacturers in general have introduced more security mitigations to stop roots from being able to completely steal all your information. So all your sensitive fingerprint data is actually stored in the T on an Android phone. And Huawei has a fingerprint agent, which we'll get to in a minute and tell you how that works. And just for a background, an untrusted app in this context is an app you just install off your phone from the Play Store. I assume that it has no special permissions. You know, oftentimes if you're on Snap, I'm sure you guys have seen it asking you for like access to logs or contacts. So none of that has been enabled. And if you know Android at all, you also know the untrusted app is the name of the SE Linux context, which an app is installed for. So it's it's a little bit in a sandbox. So we're going to be starting from that sandbox. So I had talked about the new security mitigations, but this is kind of what it looks like broken down into different trust boundaries. So on Android, you have four components. You have your normal user land where all your apps live. This is exception level 0. And there's another talk I was in that actually went over the ARM exception levels. These are kind of like rings. And then you have exception level 1, which is your kernel, which on Android is kind of like a modified version of Linux. There's with a few lines added in networking and other things to enable certain Android security paradigms. But then there's sort of this shadow world that the T implements, which has its own user land and kernel land. And in its own user land, it has trusted apps, which have the secure storage, secure payment, has the biometric sensors like the fingerprint, implements things like DRM, things that we don't want our kernel to have access to. So hypothetically, the kernel should never have any insight into the trusted apps. Even if you root your phone, everything in the blue box should be out of bounds for the kernel. Of course, it can communicate with this world, but otherwise it would be useless, but it doesn't have direct access to the apps running it like it does for apps like Chrome or the Play Store. And then finally, to support all these applications in the secure EL0 or the trusted apps, we need another kernel which can do things like load apps, map in memory, and support things like IPC. So here's how the exploit's going to work in general. Here's the roadmap. We're going to start executing code in userland. So that's the assumption that they already have code execution on the phone. That's kind of a big assumption, I know, but just for academic purposes, just please accept it. People have found bugs in things like Google Chrome and Google Hangouts. So it's you can't imagine that if you want to take it a step further, you just begin executing code in Chrome or Hangouts or a bug through one of those. And then you can begin at the stage of a stalk. So from userland, we're going to find a bug in the kernel, in Huawei's kernel, and we're going to exploit that. That will be a traditional root. That's just 2 bugs that I use, an exploit to get root on the phone. And then once we get root on the phone, we're going to take advantage of the privileges that gets us to find a bug in trusted app. And then we're going to get code execution in one of the trusted applications. From one of the trusted applications, we're going to then go one step further and finally get code execution in the actual kernel, the TOS. And with the TOS code execution, we're going to be able to find this fingerprint sensor app. So it's another application that I actually didn't have access to, and I'll talk a little bit about that later. We're going to find this application and patch it to accept any fingerprint. So a little bit more about Huawei. The T implementation is actually entirely depends on your chipset manufacturer. So Qualcomm has their own T, and Huawei also has their own T. Now, Huawei phones vary on which chipset they actually use, and this has something to do with, I think certain like baseband or cell phone stuff that I don't really know that much about, but some phone manufacturers will sometimes have their own chipset that they develop, and sometimes they'll swap them around. So there are a number of Huawei phones with Qualcomm, but Huawei also has their own chipset manufacturer called HiSilicon, which I think they acquired in 2010. This is a Chinese chip manufacturer that they now own, and they now make the Kirin chip series, which a lot of Huawei phones now use, but still not all. So the bugs that I'm about to discuss all affect the Kirin chip series, and they've actually all been disclosed as well, just as a disclaimer, and they do not affect all Android phones by any means, just Huawei phones. So the Huawei TrustZone system architecture kind of looks like this. Now, the reason I'm going over this is there's a fundamental question for you to answer is how does a normal app actually start communicating with the TrustZone and get anything meaningful out of it? Now, the first thing that we need to know is how does the normal world begin talking to it? How does the kernel talk to the TrustZone? And there's a special privilege instruction known as SMC. I believe it stands for Secure Monitor Call, that only the kernel can issue to actually make a request and interrupt the TrustZone kernel. So to handle this, Huawei and a number of other chipset manufacturers that have their own T have a kernel driver which takes requests from userland and will issue this SMC instruction on their behalf. Now, it gets kind of complicated because the kernel driver often wants to have some form of session management between itself and the trustlets that it talks to. So Huawei, in an attempt to be secure, actually has a number of these trustlets on the right implement their own form of credential checking. So secure storage can only be spoken to by my file management application. Other applications should not be allowed to make requests to it. My TA fingerprint trustlet should only be spoken to by fingerprint D, the fingerprint daemon. So the kernel driver is going to be passing credentials up to all these different trustlets, and then those trustlets in turn are going to be checking those credentials to make sure they're correct. But until we compromise the kernel, we're not going to be able to forge any of those credentials. So once we have kernel code execution and control the kernel driver, all of those trustlets, or many of them, are going to be off limits. Now, for an app to log in, what it has to do is talk to a userland program known as TCD, the T connection daemon. I believe that's what it stands for. I don't actually know. So it will actually open up a Unix domain socket to this daemon, and once it opens up that socket, the daemon is going to read off the credentials from the socket. This is something you can do in Unix. You can get, I think, the UID in the PID of your connector or your client, and then it will use that to look up actually which application itself is making the request, and then it will make ioctls to the kernel driver file descriptor that it has open. This is kind of complicated, I'm sorry. And it will do the login ioctls. Once it has logged in, and there's no way to log out, once it has logged in, the TCD will take that logged in file descriptor and send it back to the Android app through a C message, which is another thing you can do, interestingly, in Unix, or POSIX-based systems. Linux in particular, you can send file descriptors over Unix domain socket via something known as C message. So now our Android app has this file descriptor to the TrustZone driver, and it can make ioctls like you normally would to a driver to make requests, and it can send parameters up and so forth. And one more simple step, and I've already kind of talked about this, the trustlets, of course, can talk to the kernel, what Huawei calls a trusted core, and it does that through normal system calls like a normal userland app is. So this is sort of the entire map of how things are communicating back and forth in Huawei's system. Now, we're going to jump right into the bugs. And these are all very memory corruption focused. So I'm going to assume a little bit of knowledge based off like security mitigations for memory corruption types of bugs, like things like ASLR, buffer overflows, and out of bounds bugs, and what you can do with those. I will try to go over them the best as I can, though. So the first thing we do, sticking in the TrustZone domain, is we're going to target the actual kernel driver itself. Now, there are two vulnerabilities in the kernel driver which will allow us to actually get code execution in the kernel. So I've kind of already went over the responsibilities of the TrustZone driver, but something I need to mention quickly is that, and this is going to relate directly to the vulnerabilities, is that the sanitization of parameters is handled entirely by the kernel driver too, and this is where the bugs come up. So our driver needs to be able to handle sanitizing complicated data structures like memory buffers as well as integer values. Integer value doesn't sound complicated, but the buffers are. And once it sanitizes those and serializes them, it's going to be sending those up to trustlets that it chooses, and the trustlets will then act on those, and that's how the communication will occur. So a little bit about how the normal world and the trusted core agree on things like memory buffers. So the normal world is often going to want to send up memory to the to destination trustlets. Now, there's a fundamental problem here in that the trusted core and the normal world kernel don't have a lot in common by nature of this design. So your normal world kernel has no insight into the trusted apps that are running, and that's the way it's supposed to be for security reasons. So what happens is there's this small song and dance where the trusted core has a virtual address space, but it's actually one-to-one with the physical address space. So all of the virtual addresses that exist in the trusted core are actually the exact same. The values of those addresses are the exact same as the physical addresses values. So this becomes complicated because trustlets themselves don't actually follow this rule. They're mapped into their own virtual address space. And one of the reasons they do this is so trustlets can have more security via ASLR, which is address-based layout randomization. And it's a pretty standard way of making an attacker's life more difficult. So what has to happen is the normal kernel now has to look up physical addresses of any buffers that it wants to pass in to the trustlets, and it has to send those up to the trusted core. And then once it has a physical address, the trusted core can say, oh, I understand physical addresses as well. I will take this physical address, I'll map it into this destination trustlet, and now your destination trustlet can access it because I know about the trustlets page tables. I can modify them as I like. So this introduces our first problem where during the process of actually creating this physical address, we have a pretty severe out of bounds write. So, well, not an out of bounds write, but an out of bounds bug. So if I want to send up a memory reference or a buffer, I'm going to be sending up a virtual address up into the kernel. Now it needs to immediately translate this to a physical address, but for some reason, Huawei also included the option to specify an offset into this memory reference, and they never check this offset. So what I can do is I can give it a kernel address, and I can give it an arbitrary offset of 32 bits, and now I can do an out of bounds and access and specify a different physical page which doesn't actually exist in my address space. And just for those who are curious, the kernel address I don't control. So as you see, it's iterating over this linked list. it's going to ensure that I, in my own userland process, register pages and say, these are userland pages which I'm going to pass up to TrustZone. And when I pass up an address, it must exist in this list. And then it will use the correlating kernel address, which it is aware of, as one of the operands to that addition. So this allows us to specify an arbitrary physical page to pass up the TrustZone. And now, once the kernel passes up that physical page, the TrustZone doesn't know any better. It doesn't keep, while it theoretically could, it doesn't actually keep track of the normal world's page tables. So this will create an issue where trustlets will begin operating on memory, which actually exists to the kernel or belong to the kernel and not to the userland app, which is making the request, which is a pretty severe vulnerability. So as you can see, we can pass any physical address of any page mapped in, and we'll use this to write. Now, this becomes more complicated because I would also like a leak before I do the write in the kernel, so I know precisely what I want to write over. Now, here's a slightly more interesting bug, in my opinion. And this is sort of a design flaw. Huawei seems like they didn't actually know this subsystem very well. So drivers can implement a number of different system calls to, when they're being operated on as a file descriptor, and such as open and close, and they also can implement unmap. Now, Huawei implement their own unmap, and in fact, this is how you register pages that get added to the linked list, as I showed you earlier. You say, I want to unmap this page that I'll eventually want to send it to the TrustZone. And what they do is you call mmap, they call a kernel API called get free pages. This is kind of self-explanatory. It gets a number of free physical pages. It binds those physical pages to the virtual address that the Linux subsystem created for it. And then it adds it to the linked list, as we saw. Now, the big problem is they had no idea how to actually clean up this operation. So how do you clean up? A lot of people don't know how to actually clean up a map page by a custom Linux kernel driver. So their solution was to implement an ioctl. As you can see, here's some of the ioctls they implemented. If you're not familiar with ioctl, it's just it's a system call where you can send custom commands to a driver. So you give it an integer value, and then the driver will say, I know how to handle this command ID X, and then it'll have special logic for handling it. So now they have a case called shared mem release. Now there is a way to actually do this safely, but the problem with implementing it as an ioctl is that you're not actually talking to the rest of the Linux subsystem, which is responsible for managing this virtual page. So what it does is the TCNS shared memory release will actually free those physical pages. But because it actually never bothers to talk to the rest of the Linux virtual memory subsystem, it never actually cleans up the page table. So what you have in your userland process is a virtual memory mapping which now exists or now correlates to and points to a free physical page. So what happens when I free a physical page in the kernel is it gets added to a list of free pages, and this is very basic explanation of it. It gets added to a free list of pages in the kernel, and then when another application or the kernel itself wants to allocate more memory, the kernel will say, I have this list of free pages, you can just take this one. So what we can do is we can allocate memory in our userland process. We can, via the mmap, then we can issue the ioctl to free it. We still have that virtual memory page lying around, and then we can create a bunch of requests and ask the kernel to allocate more memory for us. You know, for example, by opening files. The kernel will have to open so many files that eventually will need a physical page of its own, and at that point, it's going to take the physical page, which is still bound to our virtual memory map, inside our userland process, and the kernel will begin essentially allocating kernel data structures inside our userland process, which is another giant issue. And you could use this for a lot more malevolent purposes. I just used it for leaking, but this is a pretty interesting bug. I think it's the first physical page use after free I've ever seen. So that can cause some havoc, and it's pretty fun. So as I say, with some kernel spraying, we can get the kernel data structures and get a leak. And in particular, I'm going to show you how I exploited this. So there's lots of ways to do this with an arbitrary write. This is just the way I chose. So I wanted to overwrite a file operations pointer table. So a little bit about files, how files are implemented in Linux and Unix systems in general. I'm sure many people are familiar with the file descriptor. It's sort of an opaque number, which represents a more complicated structure in the kernel. So when I open a file, I have the file descriptor, and that correlates to this giant structure that the kernel has in its own memory space, which has this file operations pointer table, which is you can think of kind of like a C++ V table. It's a way to kind of do object-oriented like things by essentially allowing you to overload a lot of different operations. So the way a file descriptor in Linux can do so many different things, as we know, file descriptors can be a socket or it can be a file, many different kinds of formats. It uses this file operations table to implement all sorts of different methods. It also contains things you'd expect the file to maintain, or the kernel to maintain, like an offset and the permissions the file was opened with. So, for example, if we open a file on a normal Linux system, we're going to have our operations pointer table like ext4, read, ioctl, and lseek. But what we want to do is overwrite that file operations pointer table and point it at a ROP gadget pointer table, which will do nasty things for us. So for those unfamiliar, ROP stands for Return-Oriented Programming. It's a way of bypassing NX, which is non-executable memory. So just because we can't introduce executable code into the kernel, we can reuse the code that is just in the kernel to do things we would like. Like, for example, I have two examples of ROP gadgets here. I have a write gadget, which will take whatever in X1 and write it to X2. These are ARM64 registers. And then return, and I have a leak gadget, which will load the value that X1 represents as an address and populate X0 with it, and then return. And X0 is the return value in ARM. So if you have X0 returned, that's the value that lseek, for example, will be returning. So what I can do once I set up this fake table is I can say lseek to this address, and then the return value of lseek will actually be the value of that address and not what has actually been lseeked. So to redirect the alpha-ops table, we're missing one piece. We have this arbitrary write, but we need a component in the trust zone which will actually do the write. So here I actually have a screen cap of IDA. So as I said, the T is completely proprietary. The chipset manufacturers have no obligation to open source any of this. So if you want to start looking for bugs in your trust zone, you have to begin reversing it. I was lucky enough to afford a decompiler, which not everyone has the privilege to do. But this is what it looks like. It's very nice. So the first thing that I found that did this is an interesting global command that anyone can actually talk to or request from the trust zone, which is command ID need load app. Now this is kind of a weird function which will tell you if you need to load an app or not into the trust zone. So I will give it a UUID, which Huawei uses as a way to recognize individual trustlets. So each trustlet has its own UUID, and their trust zone kernel will tell me, is this UUID loaded? If it's not, it will say, yes, you need to load this app. I'm going to write a 1 back into your buffer. If you don't need to load the app, then I'm going to write a 0 back into your buffer. So what I can do is I can point this buffer, as I control, I can point that at any physical page I like. I'm going to point that at my FOPS table that I want to overwrite. I'm going to begin writing a 1 or a 0 there. So I have essentially an arbitrary write 1 or write 0. It actually becomes a write 1 because these are UUIDs of values I don't know about, and I can't control the value of what I want to write to. So I have an arbitrary write 1. Now, with the ability to write a 32-bit 1 anywhere in kernel memory, how do you exploit this gate code execution? So I was fairly fortunate and I could trigger this as many times as I like. So what I did is I took this file operations pointer table. As you can see at the top, we have this kernel pointer, which is pointing to an existing ext4 file operations table, and I overwrite it piece by piece with little endian 1s to shrink it into an address that points into userland. So I can overwrite the very first 4 bytes and make that into a 1. Now the address is much smaller. Then I can overwrite the next 3 bytes, and I can make that into a 1, overwriting the original 1 that I placed. And then I can sort of even it out. This third transition actually isn't legal. I can't map that page. It's too low. There's an mmap min requirement, which stops nullity reference bugs from being exploited. So I need to write another one to bring that up to a more manageable address that I can actually map into my userland process. And at this point, we've actually now pointed an existing ext file operations pointer table into userland. So now whenever I want to make or write or read from that file or lseek on it, it's going to be using my file operations table in userland memory to figure out where those functions are implemented. So I have code execution in the kernel now. So with those ROP gadgets I showed you, I can now overwrite my cred structure. If you're not familiar with Linux kernel exploitation, that's okay. I now have arbitrary read and write, so what I can do is just say my UID is now 0, essentially. And that makes me root. So now with root, we still have 2 more stages to go. So I hope you're not bored. So these are a little bit less painful. So the we need to now own a trustlet. And in this case, we're going to be owning something known as a secure storage trustlet. This is what's responsible for transparently encrypting files on disk. So not all phones actually offer this, but Huawei has a special safe feature that they offer where you can essentially say, I have these files, and you need to put them in a special place. And the way it's going to handle this is it's going to pass the content of those files to the secure storage file trustlet, and it's going to be encrypting them with a key that your kernel has no idea about. So theoretically, this means that even if your phone gets rooted by a malicious actor, all the files you put in your safe are absolutely safe because they have no way of finding that key. Now, unfortunately, the secure storage trustlet is actually riddled with bugs, so it doesn't really matter. Now, there's one big type confusion here. And to talk about that, I'm going to have to go a little bit back into the sanitization. So the way they actually handle the sanitization of these different parameter types isn't that complicated. They have a union, which means they essentially have a data type that can be one of two things. And they have a union which can handle either values or memory references. Now, a memory reference has the buffer inside, as you might expect, and the union just has two integers that you can pass up. I imagine it's two just because the buffer, the memory reference has two values, but you can pass up an A and a B. Now, they need a way to actually distinguish between these kinds of parameter types because it is a union. There's no way to type check this. And so when they're actually passing up this payload to the trustlet, they say, I'm going to have 4 parameters, which can be either a value or a memref, but just so you can tell the difference between these two, I'm going to have an integer which can support type checking for 4 different parameters. So every single byte of that unsigned int will represent the type of each of the 4 parameters. Now, unfortunately, they never actually check param types. So I can create a secure storage file, and the secure storage file is actually kind of like a POSIX API. I can say I want to open a file, and then it will hand me back an opaque file descriptor or file handle, which I can then say I want to read or write from. So I can open up a secure storage file. Keep in mind, I have kernel code execution, so I can now log into this trustlet and begin interacting with its API. And then I can, so I can tell it that when I want to read from it, I'm going to give you an integer as your buffer argument. And since it never actually checks those param types, an integer will now be used as the buffer, and this essentially prevents them from being able to type check and make sure that the buffer address is actually pointing to a valid region. So what this causes is essentially me to read or write to any place in the trustlet itself. Now, the way this, so to give you an analogy of this would be similar to if you had a Linux kernel or any kernel that never actually checked the user land pointers that you passed in. So when I say I want to read to this address, what it's going to do is going to say the buffer that you want to read into must exist in user land. It cannot exist in kernel land. And it's going to check that against a boundary between your user land and your kernel. Now that check never occurs. So what we can do is we can just read data back into the trustlet itself and overwrite its function pointers, or we can write data out of the trustlet and leak values from within inside of it. So how do we actually exploit this? And this is a different kind of file format. It's not your typical form of a process in memory. It all exists in a weird operating context. So just through reversing, I found this tmalloc, which is kind of self-explanatory. Now, it uses a table of function pointers to implement different size classes of requests. So what I can do is, as long as I can overwrite one of these pointers with my read and my write, I can actually get PC, program counter control, when I cause a malloc request to be made. Now, there's one small problem, and like I said, I have no idea how this is actually mapped out. Through a lot of painful experimentation, I found out that there's this very weird address space layout of a trustlet. So if you remember the memory reference that I talked about earlier, they had this interesting thing where they would have to remap buffers in my userland process wanted to pass up into the trustlet. Now it turns out that these memory references that are remapped in the trustlet's address space are actually read-write executable. So this violates the property of NX. I essentially have all these buffers which I control, which have both writable and executable memory. So what this means is that I can point any of these tmalloc function pointers up into my memory references, and then my fourth parameter to my trusted call can be my shellcode. And that makes exploitation very simple. So then as soon as I get that tmalloc call invoked and I do my reads and my writes, I can get code execution immediately and have that trustlet code execution and begin writing my final stage payload, which executes or exploits the kernel. Now there's one small problem. Starting with the P9, trusted loading actually implemented ASLR, which is the address space layout randomization that I mentioned. So I don't know where the tmalloc address space is going to actually lie, but they only gave ASLR a single byte of entropy, which makes it very easy to brute force. So additionally, as soon as a trustlet crashes, these are meant to be very robust. They'll immediately be loaded back up, and they're actually put in the same exact address which they were originally loaded into. So at most, there's 256 guesses that I need to make to hit that trustlet. But even then, there's another problem in that root has access to all these log files, which just reveal the ASLR outright. So I can completely defeat the trustlet ASLR just with root because they log any crashes that are made to task storage. So if I find a single nullity reference in any of these apps, I can leak their ASLR, which is finding a nullity reference is pretty easy to do in these applications. So now we have trusted code execution. I have used the leak to actually overwrite those function pointers in tmalloc. Now all I need to do is find a bug in the Huawei trusted core itself in the kernel. So a little bit about what the TrustZone kernel does, what responsibilities it has. Again, it provides IPC. So actually when I'm making a request through the kernel to talk to a trustlet, this is actually hitting the trusted core first, so it can remap those memory references, but then also it will dispatch the call to the destination trustlet. It supports the memory address translation process, which I just mentioned. And it also has all the trustlets in its address space. So once we have trusted core access, we can hopefully find our fingerprint trustlet and do things to it, like make it accept any fingerprint. Now, there's one big vulnerability here, which anyone with kernel exploitation experience or kernel security auditing will probably be familiar with, and that is there's absolutely no pointer sanitization. So every single system call that I pass up, they'll never check those pointer values to make sure that they exist within just the trustless address space. Now, this is partly, I think, because of this weird issue where they're actually mapping the trusted core into the middle of memory instead of at the very top, like you see in a normal kernel. For example, in the Linux kernel, you have all of your userland apps in the bottom of memory at lower addresses, and then you have your kernel at higher addresses, and it makes it very easy to check between legitimate pointers, legitimate userland pointers, and kernel pointers. But because they have this trusted core in a weird location, it's not as easy for them to make this check. And I don't know what rationale they chose for doing that, but it causes problems. So this means that to actually exploit the trusted core, I mostly just need to reverse engineer the kernel and find a strange sequence of system calls which will give me a magical write what where, which is the holy grail. It means I can write any value I want to any address I want in the kernel, and that alone should be enough to get me code execution. So a little bit about the trusted core environment, what kind of security mitigations we're dealing with. There is no ASLR, or I guess in this case it'd be KSLR, but there are, and this kind of contradicts what I just said about no pointer sanitization. There are some functions which strangely do have hard-coded balance checks. So memcopy inside the trusted core does check to see if it exists within those boundaries, but almost everything else does not. There is something called PXN, which stands for page execute never. This is an ARM mitigation, which says that I can't execute code in user space. So back in the olden days, I used to be able to put a shellcode payload in my userland process. I would write a function pointer over in the kernel, and I would just say execute my kernel exploit payload in userland, and it would oblige. But it will no longer do that. ARM has protections against that. There's also no PAN, so I can access user space just fine. So this stands for page access never. If you're unfamiliar with these, you might be familiar with their x86 equivalents, which are SMAP and SMEP, which are like supervisor mode access protection and supervisor mode execution protection. These are essentially equivalents. So with the access never, what should occur is that if I ever want to access an address in userland, I have to go through a gate first. And the kernel will say, okay, I'm going to briefly turn off this mitigation, do whatever accesses you need on this user land structure, but then immediately return and make sure that any other accesses violate. So there's no gate we have to go through, which makes it quite a bit easier to do exploitation. Now, there's also no DEP, which stands for Data Execution Prevention. This is similar to write XOR X, which is you can't have writable and executable memory that exists at the same time. So this means that our kernel heap is executable, which makes it a great place to store shellcode. Now, interestingly, for a kernel with only about 9 different processes, it actually has about 300 different system calls. Now, I don't know why it needs so many system calls, but I suspect this is something to do with Huawei just completely ripping off another real-time operating system kernel that they found online that has all this functionality that they don't need. So some of these are also behind permission checks, which will stop us from having as large of an attack surface as we would like. Now, there are a number of primitives in here that exist for different system calls, and this is a little bit more of a pedantic slide. If you found the rest of the talk pedantic, this is going to be really bad. So there's no magical like write arg1 to arg0 system call, which is what we'd want. We would love to find a system call which just would take our first argument and write it to whatever address, whatever pointer is in our 0th argument, or vice versa. Now, we don't have that, but we do have other weird parameters. So we can allocate a 16-byte string we control, and we can write the pointer of that to the allocation anywhere in the kernel. That's pretty nice. We can allocate an arbitrary sized kernel heap buffer and return its address. This doesn't sound very juicy, but it's actually pretty weird. If you imagine a Linux kernel system call that would allocate a kernel heap buffer and then return that kernel address to userland, that's essentially the equivalent you would have. That'd be very strange. We can also write an uncontrolled dynamic value from a linked list into the kernel. I know that sounds odd, but this can be used essentially, we can use this at will. So once we control that linked list, we can write values anywhere we want. Now we can also copy the trustless process name to an arbitrary address. This is not as nice as it sounds because we can't change the name of our trustlet processes. There's no nice system call to do that, or at least one that I could not find. And then we have another bug, which will, via an overflow, this is nothing to do with pointer sanitization, we can get a leak. So we can now leak values from the kernel arbitrarily. Okay, so this is my most pedantic slide. I'm not going to really go over all of this. If you're curious, I suggest you talk to me about it before. But what we essentially do is allocate a kernel buffer to store shellcode in. We leak the address of our process name pointer. So we have a giant table of string pointers which have all of our process name in it. We find out where that exists. Once we have that, we're going to point this linked list to a small snippet of 16 bytes we control. So we control some of the linked list. We're going to point that to our stack, and then what we can essentially do is we're going to continue to unlink this list and get it to do arbitrary writes for us. And then once we're doing those unlinks from our stack, we're going to write kernel shellcode into that kernel buffer that we just allocated, and then we're going to overwrite a function pointer in the Huawei trusted core, which there are plenty of, and we're going to make that function pointer get executed, and as soon as that happens, we're going to be executing trusted shellcode. Now, I know that sounds really exciting, and that pretty much means we're done, but there's actually one interesting problem left, and that's I actually had no idea where the fingerprint logic actually was. So if you take your trusted execution environment OS image off the phone, you're going to get this blob with about 6 different elfs in it. Some of these are kind of self-explanatory, like your keymaster and your secure storage, but there's nothing in there which looks like a fingerprint module. For one, this should be pretty large. It should probably be larger than 100K. Fingerprint logic fingerprint checking is kind of complex logic, which will require some form of like image recognition or image matching. So where is it? So what I had to do was follow the userland fingerprint D around and see what kind of stuff it was mapping. Now the reason this is for Android to support so many different T implementations, the way an OEM like Huawei has to hook into this is they need to provide a library that gets loaded into Fingerprint D that has an API that it uses. So there was an interesting library called FPC TAC shared. I think it stands for fingerprint something, TAC trusted agent something. I don't know what the C is in either case. But it has this really interesting blob in it where it takes this hard-coded path with a UUID.sec and then it calls teak open session on that. So this is going to cause us to have, this causes a lot of questions, right? What is this? If you run a file on it, it's certainly not an ELF. It just says data. So this is actually an encrypted trustlet. Now, why Huawei felt the need to encrypt this trustlet begs a lot of questions about where Huawei got this fingerprint checking logic. I don't know. I've heard from some people they think it might be stolen, which would seem pretty likely to me, but I don't know. It's just a rumor. Now, what do we do with this? So with the trusted core code exec, we can dump encrypted memory. So although it's encrypted, we can get around that because for fingerprint checking to work, the code must be decrypted somewhere in memory, right? So since we have the code execution actually working, what we can do is crawl the address space and find any ARM instructions. So we're just going to be blindly going through our entire address space as a TrustZone kernel looking for ARM instructions, and once we find some, we're going to be looking for string references for things like fingerprint and fingerprint D and FPC, and this very naive approach actually worked in my case. I was able to find the fingerprint checking logic just via this. Once I found the fingerprint D strings, I was able to crawl up and find the ELF header and then very gracefully just extract the entire ELF. Interestingly enough, when I pulled it out, decrypted, it had symbols in it, so it was very easy to reverse. I think there was actually a function called identify image, and that logic was essentially just returned to 0 or 1 based off whether that was the correct fingerprint. So I just whipped up about 3 different ARM instructions to null out that logic and write a 0 for correct. I don't know why this was inverse, but they said 0 was correct. And then return. And once that patch occurred, we were done. That actually finished it. Now, that's essentially the end of the slides, but I have a demo. Sorry. I have a demo, so, where I unlock the phone with my nose. So, here it goes. First of all, a little bit of, if anybody actually wants to, I don't like the volunteer things. I'm not going to ask anyone to come up. But so as an example, I have the locked phone. I'm sorry if it's hard to see. I can use my index finger to unlock it. Okay. I cannot use this index finger to unlock it. I know this isn't very convincing, but it's working. So I can't use my nose either. It won't work. Now, just a second. Now I'm going to run the untrusted app. I have it installed here. All right, it's running. It's not 100% reliable. Okay. Just one more time. It just crashed, so I have to run it again. This is actually this is not a production piece of software. This is just proof of concept. So, one moment. Luckily, I still have about 8 minutes left in my talk, so there's plenty of time to see me unlock this with my fingerprint or my nose. Okay. Hopefully the second time is a charm. All right, it's running. Okay, I'm sure not everyone. Oh, Jesus. 1 second. Okay, it worked this time. Okay, so it showed me the shellfish logo, which means it worked. Now, okay, lock screen. I'm gonna hold it up to my nose. All right. Thank you. Thank you. I hope everyone enjoyed it. And of course, if anyone has any questions, feel free to ask them here or after the talk. And one small pitch. Like I said, I work for Raytheon CSI. So if you're interested in this kind of work, if you're interested in reverse engineering as a job, or writing exploits as a job, or looking for bugs as a job, come talk to me. I know it seems like a crazy thing, but people do pay you to do that. So if you're interested, please let me know. And yeah, you can work for us. Okay, thank you. Any questions? Yeah.
So once you're in the trusted core, can you like do anything to the baseband firmware, and can you like change it if you just?
You can. Excuse me. I have played around with it. And you can modify. Oh, what? Okay. All right. So the question was: once I'm in the trusted core, can I essentially play with the baseband firmware, the baseband memory, and do things like blow E fuses? Now, I haven't played around with the E fuses, but you can read and write from the baseband memory that's loaded since it exists at a physical address. I think that could differ depending on, something I actually don't know that much about, but I have played around with it on this Huawei phone, and I was actually able to read memory out of their, I think it's their Belong modem, and write to it as well. So it is something, it is an interesting research, introspection technique that you could use, yeah. Any other questions? Okay, thank you everyone.